apparently. Okay, I'd like to start by thanking the organizers, Wister, Jacob, and other organizers for organizing this workshop. And as Uli already said, my name is Akash, and I'm a postdoc in the group of Professor Belzig at... Someone knows Jacob's password? But how does this happen?
I don't know.
Yeah, he's just playing jokes on me, I know. Okay, once again, so I'm Akash. I'm a postdoc in the group of Professor Wolfgang Belzig at Constance. And this morning we have heard about, even just now we've heard about the role of magnons in the spin transport process in different phenomena. Particularly, Gavit presented a very good and broad overview of the different systems and processes where magnons play an important role. I'm going to take a step backwards, and I will be discussing just what a magnon is in somewhat detail. So to start with an analogy, we know light as an electromagnetic wave in the classical sense. And once you quantize all the fields from theoretical perspective, you quantize the Hamiltonian, and from a practical perspective, you think of it as particles, then you talk about photons. So magnons is nothing but the quantum quasi-particle that corresponds to spin waves, which is what Landau-Lifshitz-Gilbert equation describes. So as far as I kept track of the talks, whatever we've heard was more or less LLG equation dominated. So I'm going to use different formalism. I'm going to change gears and go to the quantum limits, and I will be focusing on magnons, or strictly speaking, the excitations, the normal excitations in a ferromagnet. So let me just give away the main message in the beginning while you're still awake. So in the next 25 minutes or so, I'll try to convince you that in contrary to what we have been seeing in some literature and also the books, which in a very simple model say that magnons are spin h-bar quasi-particles, I will try to argue that that's not true in general, and the low-lying magnons, low-energy magnons, have spin different from h-bar. In particular, the magnons that you excite in ferromagnetic resonance do not have spin h-bar, but it can differ from h-bar by 100% easily. And I will also try to argue very briefly that this non-integral spin is only one of the manifestations of a quantum phenomenon, which is known as squeezing in the quantum optics community. So basically, I'm trying to draw a direct analogy from classical optics and quantum optics, which has become a very mature field in the last 30 years, starting from I think the 70s, quantum optics started to evolve. And I'm going to use that, just give the analogies in the same way how one can use those developments and transfer them from classical magnetics to what one hopes that can be quantum magnetics or quantum magnetism. Okay. And then in the end, I'm going to show how this non-integral spin is measurable via non-equilibrium noise. And I'm presenting my talk, I'll follow the reverse trajectory. I first talk about noise, we calculate the noise, and then we find a non-integral spin, and then we go back to see what other properties are offered by these new excitations. Okay, so let's look at just a simple DC charge current. Nothing about spin here. So if I think of a DC charge current, the picture that comes to my mind is this. Because it's independent of time, you should have a current that stays the same. But if you go to an experimental lab, that's not really how it looks like. It's a lot of crap coming into the oscilloscope. And then you say, okay, well, you know that at finite temperature there is noise because of thermal fluctuation, so you decrease the noise and it becomes a little bit better. But then, just for the sake of argument, just to test the limits, we go to 0 temperature, and then it starts to look like that. And these peaks are a result of the fact that at the microscopic level, the charge transport is not a continuous process. It is taking place in one step at a time. So one electron at a time is entering your system, and hence it's inherently quantum and discretized in nature. And this is called short noise, and this has been investigated for electric current for a long time. And each of these peaks represents a single charge transfer event. Now if we had equipment to directly observe these peaks, so these peaks are at the femtosecond time scale. So if we had good equipment with that high response times, then I should just sit down and not talk further. But since we do not have equipment that can observe charge current in real time with this precision, the question arises, how can we gain this information without having this high precision? And the answer to that is we study the fluctuations in current. We try to study the properties, because if the charge current was completely constant, there will be this quantity, the fluctuation in current will always be 0. But since we can study the fluctuations, we should gain some more information than is provided by just the DC charge current. I'll show some equations, but if you don't understand, it's not really important. I'll just do that for completeness. So don't worry if you are not familiar with the equations that I'm using. So one can define a noise power spectral density, which is defined. So this is a quantity that experimentalists measure, and this in the Fourier space can be written as an integral over a quantity which is defined as power spectral density. And theoretically, this power spectral density is the Fourier transform of what is known as a correlation time. So this tells you at what time the current loses information about its own origin and so on. So now let's go to the another term, which is the Poissonian transport. So let's consider a very simple system, like I showed you the DC current. Okay, if the underlying particles, which I continue to call electrons for now, if they're not talking to each other, it is a fair assumption that the probability of each charge transfer event is independent of what else is going on in the system, because they're not talking to each other. And to such an assumption, one can say the probability per unit time of charge transfer is constant. Well, that's a very general thing. And based on this general thing, one can answer a different general question. The different general question is, given a certain measurement time, how many charge transfer, what is the probability that n charge transfer events will take place in this short time? And just using this assumption, one can derive that the answer to this is, so Pn is the distribution, the probability that n events will take place, and one derives that this gives you a function which is called the Poissonian distribution, and hence this transport is called Poissonian transport. One of the features of Poissonian transport is that in this case a fluctuation is equal to the average value, and using this once again very generally, one can show that the low frequency short noise is directly given by 2 times the quantum of charge times the DC current. And this gives us a very powerful tool now to gain some information from the fluctuations, as well as to probe the transport at a microscopic level. Because this is an experimentally measurable quantity, this is an experimentally measurable quantity. You just divide the two and you directly get the quantum of transport. So that was a simple case for a non-interacting system where the constituent particles are not talking to each other. But to give a couple of extreme examples, I will just show that this short noise has been very useful in many systems. One of them is a superconductor normal metal junction, in which the short noise measurements show that the quantum of transport is not an electron but 2 times an electron, which is because we know that the Cooper pairs are formed in superconductors and so on. Similar determinations have been done in fractional quantum Hall effect, but I think you get the point that you can determine the quantum of transport using these measurements. And I only cite 2 of the examples which are extreme, but this is a very extensive review article on short noise and how helpful or how powerful it is in finding out the microscopic dynamics of a system. And now, this was all about electric currents. Now, with the advancements in technology, and since we are all kind of attending a workshop called SpinCaT, I don't need to convince you that spintronics has evolved into a very applied field, and we have made significant progress in experiments over the last 1 decade or so that we can really measure spin currents. We are getting very close to measuring them on a regular basis. And hence, a natural question arises, can we use these short noise techniques to get something more out of our spin current systems, not just the charge current, but the spin currents? And the answer is yes, and that's what the rest of this talk will demonstrate. Just to give some motivation, well, I don't think we need too much motivation, but still I'd like to motivate why this structure. So this represents a ferromagnetic insulator where the ions are attached to the lattice, and this represents a it's a conductor which has itinerant electrons. So I just want to say why this system is exciting, which as Gavit showed, was used almost in every setup, including what Ulrike showed. So the idea is that this ferromagnetic insulator hosts excitations which are bosonic in nature, so which are fundamentally different from electrons, and also they're quasi-particles, and they are massless quasi-particles, so they are not conserved and so on. So this offers possibilities for doing stuff which one cannot do with electrons. And that's why it's interesting to think of magnonic systems. And why this conductor? Because this system does not have any electrons, the charge conductors, and this system does not have any magnetic excitations, but via an interaction at the interface, one can transfer the spin current from this system to the conducting system, and the advantage of that is, as Thierry Vallée said, that the existing technologies are really hard to displace. So the advantage of that is we have a huge expertise in dealing with electronic systems. So if we can inject the measurable quantity into an electronic system, that opens up a vast range of possibilities to what you can do with it. And that's why this system has been extremely exciting and continues to be a subject of a lot of activity. And just to justify noise, without getting into details, I just want to point out that using very modest setup, which were found lying in a closet in Munich, they were able to measure thermal spin current noise in that system. Okay, so let's go directly to what a magnon is, which is kind of the central issue that we're addressing. So if I consider only exchange interaction and Zeeman energy, which is most often the case. I mean, as far as I saw the Hamiltonians, Ulrike also had only these two terms, right? Exchange interaction and Zeeman term, and anisotropy, yeah, okay. But anisotropy can be effectively incorporated into Zeeman very often. So if I consider only these two terms, so my ferromagnet can be in equilibrium, can be represented schematically like that. But we want to look at non-equilibrium, so let's see the lowest lying state will be if we flip one of the spins, okay? And just like in a semiconductor, it's easier to consider a hole as a quasi-particle instead of looking at all the electrons which form the valence band. It's convenient to represent this spin flipped as a equilibrium background on which a double spin flip has been superimposed. And this double spin flip with spin h bar is called a magnon. At this point, I will clarify terminology. From this point on, whenever I say magnon, it will mean exactly this quasi-particle, which has spin h bar. And then I will show later that this is not what forms the eigenexcitation in a ferromagnet, which is also typically called magnon because distinction has not been very clearly made. Okay, and it's important in this case. Okay, so we have this magnon quasi-particle, and what one can show is that this magnon quasi-particle, delocalized over entire space, is the eigenexcitation of the ferromagnet, given that one only considers exchange interaction Zeeman energy. Okay. Now I will introduce the theoretical machinery, but if you don't follow, you don't have to, it's not important. So one can describe, first let's look at the classical Hamiltonian, and one has the contribution from the Zeeman term, anisotropy, exchange, and the dipole-dipole interaction. This is a term that will play a major role in the results. So we linearize about equilibrium orientation, which means the magnetization is along z direction. And I will not motivate these terms. These are pretty standard, can be found in the literature. So this is how, in the linearized limit, the Zeeman anisotropy terms looks like. This is how exchange term looks like. Obviously, exchange term costs you energy if the magnetization is changing with space. And the important thing is the dipole-dipole interaction can be considered in a mean field way by saying that, okay, I have a magnetization. This magnetization generates a field. And this field interacts with itself. And that's how you can incorporate this interaction terms. And that's why this half factor is included, because otherwise you will have double counting. This is also what people have done in electronic systems for like in the DFT or any kind of interaction effects. And I will not go into detail this derivation. I encourage you to look at the paper. But the idea is that you can split the different components into the uniform component, spatially uniform component, and spatially non-uniform components. And the spatially uniform is very easily and directly related to the magnetization. So the demagnetization, this field, the uniform component is directly related to the uniform components of the magnetization, and the constants, proportionality constants, form ideally a tensor, but in the most systems you can diagonalize the tensor, and it has 3 components. Okay. So these will be relevant for us. I will not be looking, at least in this presentation, at the non-uniform field effects, although they are important. Okay, once again, if you are not familiar with Haussmann-Primakov transformations, then don't worry, this doesn't matter, but just for completeness, this is how Haussmann-Primakov transformations look like. You can relate now we are quantizing the system. So the side of classical Hamiltonian, we quantize it just like one does in electromagnetics. I can express my magnetic quantized variables in terms of bosonic annihilation and creation operators, and actually I will stick to the linear limit, so that ugly factor is not relevant for our case. Eventually you end up with this Hamiltonian. Here B is the annihilation operator for a magnon. So now by magnon I mean spin h bar quantity delocalized over all space. So this is a magnon with a unique wave vector, in which case this is the wave vector is denoted by q. Okay? And these ak and bk, which are the only 2 constants that enter, they can all be expressed in terms of the quantities I have introduced earlier. And since I'm going to disregard non-uniform effects for the moment, I mean they're not relevant. I'm not disregarding as an approximation. I'm just not going to look at non-zero q excitations, and you can look at the paper for more details. And then everything is determined in terms of the constants that we know, so there is no approximation at this level. Okay, now we go directly to the punchline. The punchline is these terms are purely the effect of the dipolar interaction. And this is exactly where the difference arises, because I said in most of the literature and even in textbooks, people use a simple model, which is fair, because for most cases it's not important to include dipolar interactions, but for some it is. And when you only have exchange and Zeeman energy, this is the Hamiltonian how it looks, and this is already diagonalized, which means that the magnons are the eigenmodes of the ferromagnet. However, the moment you consider dipolar interaction effects, these terms make it not the case. And you need an additional step to diagonalize a Hamiltonian, which is the Bogly-Bov transformation. And this I really like to point out, because since I'm in a group which focuses on superconductors, the Bogly-Bov transformation was done in 1955 by Bogly-Bov, and it was already done by Haussmann-Primakov in 1940. So magnetic community wins. So although this is called Bogly-Bov transformation, you can basically you define a new excitation in terms of the old excitation variables, and which brings your state to diagonal form. So the message of this slide is that the magnons are not the eigenexcitations. The eigenexcitation is a new excitation, which I call squeezed-magnon. And I will clarify, I will justify the terminology in a short moment. Well, now we have understood, at least diagonalize, obtain the ferromagnetic insulator Hamiltonian. Now the full system that I want to study is that I showed in the beginning, the ferromagnetic insulator and a conductor. To describe the system, I have to take into account the Hamiltonian, the ferromagnet, the conductor, which is just a sea of electrons, the interaction at the interface that allows transfer spin from one to the other, which is just an exchange interaction at the interface, and finally the driving term. So what I'm going to do is there's a static magnetic field which saturates the ferromagnet in one direction. At the same time, there's an oscillating magnetic field that excites the system. So if you're familiar with the field, this is basically a standard spin pumping experiment or with ferromagnetic resonance. Once again, there are expressions for everything, but I will just skip them. What I want to emphasize is that I solved the equations of motion, the quantum limits, the Heisenberg equations of motion. In the steady state, this is my result. So I'm just looking at the dynamics of the, since I only drive the uniform mode, Q equal to 0 mode, that is the only one that becomes non-zero, and it, in the quantum terminology, it is in a coherent state, which simply means that it is it's kind of a classical state, which basically means that I have this expression where the mx is given by the real part of this term and my by the imaginary part. And this is exactly the same as if you would have solved the ferromagnetic resonance problem with LLG equation. And I can also calculate the spin current injected into the normal system, and that comes out to be this, which is once again just restating what we know from the spin pumping. So it's equivalent to the spin pumping terminology if one translates the coefficients from one to another, which have also been done by other co-authors, like Sarkovniak has done it, Maikawa has done it, so there are 3 or 4 papers which have done this. Okay, so now let's go directly to the short noise, which is, I would say, the first real new result. So you calculate the short noise, and it comes out to be this. So as a function of frequency, it looks something like this. I directly look at the 0 frequency short noise, and now this is suspiciously similar to the final the expression that I showed you for Poissonian transport, that you have the noise given by 2 times the quantum of transport multiplied by DC current, and this is exactly what you have. So what this tells you is that in this process, the quantum of transport is h bar star, and h bar star is not h bar, it's something else, and I will show you in a moment. So this is what it tells you, that the eigen excitation, so for ferromagnetic resonance, you had this Squeezed-magnon, so Q equal to 0 Squeezed-magnon. It basically tells you directly that the quantum or the spin carried by the Squeezed-magnon is not h bar but h bar star. And actually this is how our research progressed. We actually first wanted to calculate noise, and then we got this result. Then we were thinking, well, this is strange because we always thought the spin is h bar, but it's coming out to be different. Then we went back to equilibrium stuff, and we realized, well, in some sense, once you look at it, it becomes obvious. And this is the obvious part. So h bar star is given by h bar. It's always larger than h bar, and the fact that it's always larger is intricately related to the bosonic nature of magnons. So it's also a quantum effect. And this delta is always positive, and I have expression for this delta in terms of A and B. It's analytically available, but it's complicated, so I will not show you this now, but I will just show you the plots in a moment. But what I'm trying to emphasize here is that even in the original paper by Holstein and Primakov, which was the first good attempt at a quantum theory of magnons, they did not do this, but you could directly use their formalism to obtain this non-integral spin. So if you simply calculate within their formalism what is the total spin of the system, this is what it would be if there is no excitations at all, okay, or there is no 0 temperature and so on. And this is the reduction in the spin because of the magnons. So the spin h bar basically comes from this equation where the dipole interactions have been ignored, and that's why this term is 0. By the way, this term is just from this Bogoliubov transformation. So this, if we did not need any Bogoliubov transformation, this VQ conjugate will be 0, identically 0. So you see that because of this term, the spin current, spin quantum changes from h bar and it increases. And this also tells you that this only increases, does not decrease. And this is the so-called vacuum noise. This has also been commented upon in the same paper, but they use a very classical approach to derive this. And this is, by now we know, which was not known at the moment, this is a direct consequence also of something called squeezing that I will talk in a moment. Okay, so if I now try to put numbers and I take a specimen in the shape of a film, which is the most common geometry, then I have these plots. So on the right-hand side, you see the ferromagnetic resonance frequency. On the left-hand side, you see the enhancement in the spin compared to h bar, the fractional enhancement. And then I do it for yttrium iron garnet, which is the material of choice, as Gavit suggested today, and then iron, which is a conventional magnet, and it's relatively strong. So you can see that if we have a 5 gigahertz cavity, so usually experimentals, how they work is they choose a frequency, and then they tune the magnetic field to achieve ferromagnetic resonance. So if we have a 5 gigahertz frequency cavity, you see that you get this field, and corresponding to this, the delta enhancement in spin for YIG is something like 0.15 or something. Okay, and if you choose a 2 gigahertz cavity, which is also very common, you have it slightly like 0.5. And on the other hand, for iron, if 5 gigahertz cavity means that this enhancement is 4, so 400% enhancement. And this is understandable because the dipole effects are stronger when the magnetization is stronger, and for iron, the magnetization is probably the strongest amongst all magnets. The message of this slide is that this delta is not a perturbative effect. This is not something that is 0.1% or something. This is of the order of 1, and it's for metallic magnets, it's bound to be larger than 1. Okay, so that's, in some sense, that's the first message, that you have non-integral spin-magnons, especially at low frequencies, especially ferromagnetic resonance magnons, and one has to be careful about this. On the bright side, this offers many quantum possibilities because the squeezing, one can directly borrow a lot from quantum optics. And since I don't have too much time, I will just give a couple of slides on squeezing, but in the end, it's a completely different subject. So I would just throw in this word, and I would encourage you to look it up. So the idea about squeezing is that if you have two operators which do not commute, okay, just basic math, and then they follow this, the Cauchy-Schwarz inequality, that the fluctuations in one multiplied by the other are always greater than this one. This is the mathematical statement of Heisenberg uncertainty principle. And typically in quantum optics, what they define is they define two quadratures like that. And then these two do not commute, and on this side you have a constant. In our case, mx and my take the role of the two quadratures. Okay? And then is a bunch of math that one can define a squeeze operator. And when one applies squeeze operator onto a vacuum, one obtains squeeze vacuum. And this has many quantum mechanical properties. And I cannot possibly do justification to this subject in a short while. So let me just better skip over it and simply point out that this is one of the definitions of squeezing that's used in quantum optics. This is one of the general definitions of squeezing that is used in quantum optics. And what we show is that the magnetization follows exactly the same relation. So that is a direct comparison that you have squeezed magnetic states. And once you accept this, once you make this analogy, everything that has been done in quantum optics on the squeezed states, you can find long chapters on quantum optics books on squeezing, and then you can transfer all that information to magnetic systems. And what I cannot, I definitely cannot describe here is that for I've been talking about the Q equal to 0 magnons, but when the Q is not equal to 0, you have something called two-mode squeezing, which is even more complicated, but also offers more sophisticated possibilities, and which has been realized in quantum optics on a regular basis. So it's very much has been done in quantum optics. Okay, so I will skip finite temperature noise anyway. So we have been talking about 0 temperature, by the way, but the finite temperature noise calculation demonstrates that temperature is not an issue. Temperature, in this case, from electronic systems, we know that for observing electronic short noise, you need low temperature. But here, because of the bosonic nature of magnons, the finite temperature does not impede. So the short noise is much larger than the thermal noise at reasonable temperatures. Like this is for 10 Kelvin, and you can see already that at 10 Kelvin the thermal noise is below 10 power 18 in some units, and the short noise is above 10 power 19 in the same units. Okay, so with this I would like to conclude and summarize which I tried to allude to. So first of all, dipolar interaction gives rise to squeezing of magnons. It was not relevant. The magnons which are so far up in the energy, for example, in spin-Seebeck effects, usually you have thermal magnons, which means the dominant energy comes from exchange. And then this will not be relevant. But as soon as you talk about low energy magnons in the gigahertz regime, there the dipolar interaction is very much important, as has been known already for a while. But this directly affects the spin and other properties of the magnon and gives rise to squeezing, which is an exotic quantum phenomenon known from quantum optics. So that I covered all these 3 points in that statement. And finally, I did not have time to show this, but in this case, because of the bosonic nature of the magnons, the short noise actually dominates over thermal noise up to 100 Kelvin or so, and there are reasons to argue that it could dominate all the way up to 300 Kelvin, but the theory that I use is strictly speaking not valid at those high temperatures. That's why I don't make a concrete statement. But certainly at 50 Kelvin or so, everything is valid, and I can assure you that short noise dominates thermal noise. With that, I thank you for your attention, and I hope you have fun tonight at conference dinner.